I'd like to do today is a couple of things. I'd like to help you get a deeper understanding of dark matter and dark energy, because there's a lot of subtlety there, and I think you can understand it, but there are some subtleties. I wanted to model maybe a little bit to journalists how I found it effective to talk to the public about these. And I also wanted to go through and maybe tell you things to watch for in the future and questions you can ask, because dark energy, everybody and their uncle is working on dark energy now. It's a very popular thing, and you're going to see a lot of results, but some of these results may not be as exciting as the PIs think they are. You should know how to ask those questions. But I'm going to start out with the modeling a little bit. How do you discuss this with people? And it's getting back to what are the big questions. Cosmology asks the big questions. I like to say that humans for millennia have been looking up at the sky and saying, what's out there? What's out in the universe? How did it get there? Where did we come from? Where are we going? Those are the questions of cosmology. And a problem that cosmology has and astronomy has is that except for the solar system, we're not an experimental science. We can't do experiments. We just have to take whatever junk falls out of space on the Earth and analyze that. That's all we can do. And most of the junk that we look at is radiation, particles of light, and that's why we like these big telescopes. These are nothing but big photon collectors, okay? And we pay so much for them. The public wants to know, why do you have to buy a bigger telescope? We want to be able to collect more of this junk to be able to analyze it, the light coming out. All a telescope does for you is give you more light. That means you can see things that are farther away and dimmer, and it lets you zoom in to look at it. It's remarkable that we've put together this whole theory of what the universe is, cosmology, just from mostly electromagnetic radiation coming from space. These are the optical ones, some of the best opticals and the ones we dream for. But we want to look at all the photons, all the light, so we use all the parts of the electromagnetic spectrum, ALMA, and I think for science journalists, you should really be looking at this. This is a tremendous step forward. There's going to be some amazing discoveries coming out of this one, because it's maybe of the things up right now, just turning on, pushing us the further out. We need X-rays from the Chandra X-ray satellite and gamma rays. The public always thinks we go to space so we can get closer to the stars. No, we just want to get above the atmosphere so we can have this light in a more pristine state. Of course, we see all things, and hopefully we'll be looking at JWST in the infrared as well. So what do you see when you look out in space? Dark energy and dark matter, you don't see those. What you see are stars. And when you zoom in using Hubble Space Telescope, you can see stars being born, which we've discussed. You can see stars dying in supernovas, as we've discussed. You can see groups of stars. Is this thing working? Yeah. Groups of stars, like an open cluster of stars, like the Pleiades. You can see globular clusters of hundreds of thousands of stars, like M3. But mostly what you see are these things, galaxies. We know, and we've heard many times here, the main denizens of the universe are galaxies. That's how stars live. And we've learned that galaxies come in different types. There's these disk galaxies, our favorite one, NGC 4565 with a bulge and a disk. And we see all different kinds of galaxies, big bulges, little big disks. And we see also that these denizens galaxies come in groups. They come in groups of several small groups like this. And when you see these pictures, when you see these diffraction spikes, those are stars. And all the fuzzy things that are resolved are galaxies. So you can just, if you see these objects, pay attention to the stars. These are not anywhere near the galaxies. They're right nearby in our own galaxy. These are far away. So galaxies come in groups and clusters. This is the Coma cluster of galaxy. Can you see this? Are there any stars here? There's one, but pretty much thousands of galaxies here, all stars. Okay? So this is what we see. Okay? Stars and galaxies from our pictures. If you take a blank area of the sky, the size of a grain of sand, this is the Hubble Deep Field. There's a star because of the diffraction spikes. So we see that the entire sky is filled with galaxies. That's it. Okay? Now, if you look at these galaxies, the little ones here, they're very odd. Okay? They don't look like normal galaxies. And this is a blessing and a curse of astronomy that you've heard about many times in this conference. When you look out in space, you look back in time. Okay? So these galaxies are funny here because you're seeing back in time. You don't see the sun like it is now. You see it like it was 8 minutes ago. And how I like to talk to the public about this is I ask them a question. I say, suppose there's a very advanced civilization 65 million light years from us in a galaxy looking at us on Earth. What are they seeing today? And then I wait for the answer. They're seeing dinosaurs. So they don't have to guess about dinosaurs. They can actually see it. So we don't have to guess about the past. We can see it. And that's how you can explain the microwave background. You can say, suppose we say the universe is 13.7 billion years old. If we can look at light that spent 13.7 billion years getting here, you can actually see the Big Bang. And so we've seen a picture of it. The Nobel Prize was given for this picture a few years ago. Okay? So that's it. I've kind of showed you everything. Where's the dark matter? Where's the dark energy? Okay? So the point here is that you don't see it. You have to go and use some theory. You have to use some other kind of things. You don't just take images. You take spectra, and you've seen these Keck spectra before, actually. And the dark lines here tell you two basic things. The pattern of these lines tell you exactly which atoms, which elements, which molecules are sitting in the gas being absorbed. And the motion of these lines, if they're shifted from the lab values, tell you the speed, the Doppler effect. So you can measure what's in anything that you can take a spectrum of, and you can measure how fast it's moving. That's where the dark matter comes from. You take a spectra of this side of the galaxy, and you see it's moving towards you at 500,000 miles an hour. You take a spectra of this side, you see it's moving away from you. You see it spinning, and then you use theory. Okay? Dark matter comes from theory, the theory of Newton's theory of gravity first, and then Einstein's. And the 500,000 miles an hour, it's not just here, it's for gas way out there. And you need to have much more mass there if you want to use Newton's theory. The alternative explanation for dark matter is that Newton's theory is not working. Newton's theory tested here on Earth works very well, works in the solar system. Does it work on thousands of light years? Okay? Well, we don't know. It's an experimental question. Okay? So the picture we have, either Newton's theory is wrong, or there's dark matter, or the experiments are wrong. And for the first 40 or 50 years of dark matter, people took that latter one. They said, well, your experiments are not quite right. You're not doing things right. Finally, as we heard from Sandy Faber's paper, famous paper, people said, OK, we believe the experiments now. We've got to either change Newton's laws, or we're going to have dark matter. I think nowadays this question has been solved in favor of the dark matter. And the reason is a new technique in astronomy that all journalists should know about because it's becoming more and more popular, more and more important, and it will continue to become more important, is gravitational lensing. Okay? Now, I'm putting up an equation. I'm going to put up a few equations for you. I understand that journalists, you're not going to put equations into your writings. But I think you as journalists will understand better if you look at the equations. Okay? So this is the equations of general relativity, light bending. So general relativity says that there is no force of gravity. We've heard all the speakers talk about force of gravity. They're being a little sloppy. In general relativity, there's no force of gravity. What there is a curving of space-time. So if you put a mass here, it curves space-time. And then light and other particles go as straight as possible as they can, called geodesics, through the curved space-time. So you can see from this picture, if I put a massive object there, light from this source can get to you two ways. That will make two images. That's called gravitational lensing. Okay? And the formula is important. It's not just, this is derived straight from general relativity, but what's important about it is the bending angle, the angle that the light bends, is proportional to the mass. The bigger the mass, the bigger the bending angle. And it's also inversely proportional to the impact parameter, the distance there. So if it comes closer to the object, it'll bend more. Why does that matter? Because you can measure the impact parameter and the angle, and then you can measure the mass. Okay? Now that is the actual mass. That's not the mass in atoms. That's not the mass in, it's the total mass. It includes dark matter. So here's how we can actually get a measurement of dark matter, though we cannot see it. Okay? Dark matter does not seem to emit or absorb any kind of electromagnetic radiation, but it will curve space-time. That's its main effect. And so we can do it by gravitational lensing. Okay? So in a picture like this, Abel 2218, you can see a galaxy like, it's kind of hard here, like here. That's actually a very faint galaxy sitting right behind. This is a cluster of galaxies, and that same galaxy is appearing here, and I can't tell from my angle here. You can see it up here, here and here. So you can measure that light bending angle. That's a little galaxy right behind. You can measure that impact parameter. You can measure the angle. You can measure the mass. And you get not just the mass of stars, you get the mass of everything. And when you add up that mass is way more than the mass of stars. Okay? So this is kind of a measurement of dark matter. But actually, it's not really true in a certain sense. I'm showing you a nice picture here of stars. In fact, in clusters of galaxies, most of the atomic mass is not in the stars. It's in a hot gas that's emitting in X-rays. It's not glowing. If I took an X-ray picture of this cluster, I would see that. So in fact, you have to actually include that. Okay? So this is called strong lensing whenever you get two images, and it's a good way to measure mass. There's another way, but it only works if you get something very closely aligned up. If you want to know the amount of mass way out here, you can't do it from strong lensing because there's not two images. So another technique has been developed. And again, we're going to get to dark matter and dark energy. You're going to come back. These are the techniques that are being, proposals are being made, very expensive proposals to do this kind of measurement of mass. And this is why we want to do it. So these are little Hubble Space Telescope pictures around this cluster of galaxies. The cluster is here, the name of it. And each one of these little things is that Hubble Deep Field-like size of a grain of sand at arm's length, a tiny little region of the sky. They're not measuring lots of images of these galaxies, but they're looking, the mass here distorts the images a little bit. It stretches it in the tangential and squashes it in the radial. And by statistically measuring thousands and thousands of galaxies being stretched and squashed a little bit, one can use that light-bending formula repeatedly, right, with a computer, and you can reconstruct what mass must have been here. And that's what this is. This purpley thing is a reconstruction, mathematical reconstruction from that light-bending angle of where the mass is. And the mass is this big blue blob, much more mass than in all the stars and in the galaxies. So you have kind of a pseudo-image of the dark matter, and it's the dark matter mostly doing it. So even in this case, this now is Einstein's theory being used to see the dark matter. Even in this case, you could make a theory that just modified the way the light-bending formula works and said, OK, you're still using theory. You still haven't convinced me that it's really dark matter, something that we can't see, and not just a change in the laws of physics. What really convinced a lot of us that dark matter is real and not just a change in Newton's laws or Einstein's laws. Keep in mind that Newton's laws of physics derive directly from Einstein's. If you throw away Newton's laws, you're also throwing away Einstein. Okay? Is this image. This is three superimposed images. This is the bullet cluster. And this is what really convinced us that we must have dark matter. You've got three things. You've got the stars from Magellan, the galaxies here. The pinkish stuff is the Chandra X-ray image of this region, and it's the hot X-ray emitting gas. And that's where most of the atoms are. Most of the atoms aren't in these galaxies. There's about 5 times more atoms in the hot X-ray emitting gas than in the galaxies. Okay? And then the dark, this purpley thing, is actually the weak lensing analysis, which tells you where the actual mass is. Okay? So what's happened here is this is called the bullet cluster, because one cluster has gone shooting through another cluster. The hot gas shocked, there's a bow shock, and kind of went through it and slowed itself down, because gas, when it hits other gas, just kind of goes, whoa, and interacts. Dark matter, being weakly interacting, or at least not very strongly interacting, just goes right through itself. Okay? So what you see is you've managed, finally, to separate the dark matter from the atoms. The atoms are all sitting right here in this hot gas, and the main mass, by the lensing, is over here. So now it's almost impossible to think of a way to explain this without extra actual stuff. So because of this picture, we're really pretty convinced that dark matter is real stuff. It's not atoms. We know that from completely independent lines of thinking with the Big Bang nucleosynthesis. We know how much atoms there are in the entire universe, and also from the WMAP. So we think that dark matter must be actual stuff. It can clump. It can move around like gravity, but it's just some kind of particle we don't know. So it exists. There's 5 times more of it than atoms. There's lots of ideas. I'm not going to go into this. I think Manoj is going to talk about this. It's a fantastically interesting and exciting area because there's a lot of experiments. There are dozens and dozens of experiments. So as journalists, we may actually in the next few years have a detection, but it's possible that we will never know what it is. The dark matter could be some kind of particle that only interacts gravitationally, and we'll never know what it is. We know as much about it now as we ever will. That's a possible answer. This is science. We just don't know. So that's all I'm going to say about dark matter, because my task is dark matter and dark energy. And I think we've done quite a bit about dark matter. We have Manoj coming up. So where's the dark energy in all that I showed you? Okay? Well, it's even more subtle. We have to go back to the Hubble Deep Field here, and we do take the spectra of all these galaxies to find out how fast they're moving, and you find out that they're all moving away from us at very fast speeds. This is the expansion of the universe. So how do you understand the expansion of the universe? You cannot understand the expansion of the universe without going to Einstein's theory of general relativity. There are people, especially as journalists, people will give you these explanations of gravity slowing things down and force of gravity. That's not the real explanation. If you really want to understand this, you have to learn a little general relativity. So here I'm going to show another equation. I know as journalists, you're not going to put these equations into your movies or whatever, but you yourself should stare at these, because your understanding, if you understand this is high school geometry level understanding, but if you do it, you'll understand it at a deeper level than most PhD physicists, okay? So here, what Einstein's theory says, it replaces gravity as a force with curvature. It says the local matter and energy density curves space-time, and that is the way you mathematically describe curved space-time with something called a metric. This is the metric, okay, of flat space-time. The metric is nothing but the Pythagorean theorem. If you have 2 galaxies separated by one here and one here, you want to know the distance between them. That's on the left-hand side of the metric. You just take a squared plus b squared and the square root. That takes the difference. In flat space, the metric is just the Pythagorean theorem. Okay? You can understand this. This is geometry. But what Einstein's theory does is you put in the matter and you solve for the metric. Okay? Now, Einstein did this. He plugged in a uniform density of stars. He thought stars were the main densities of the universe. We know they're galaxies. So we put in a uniform sea of galaxies, and you solve for the metric. Here's what comes out of Einstein's equations. This part here is just the Pythagorean theorem again, but there's this factor called r of t, called the scale factor, which is in front. This factor goes like t to the 2/3 power. This is a remarkable result. This means this is the distance between galaxies. This says the distance between galaxies increase even for galaxies that are at rest in their local frame. So you take 2 galaxies, no force between them, they're just sitting there, and after time, they're farther apart. Okay? This is not what most people think the expansion of the universe is. Most people think it was an explosion that happened sometime, driving everything apart. That's not what's happening. They're sitting at rest, and they're getting farther apart because the metric is changing. This understanding, thinking this way, really can help you answer questions that the public asks all the time. For instance, they say, what is the universe expanding into? You know, it's getting bigger. Is it expanding into new space? Well, it's clear from here it's not expanding into anything. They're just sitting here, and the distances are increasing, right? So when this distance goes from 1 million megaparsecs to 100 million megaparsecs, it's not going anywhere. It's sitting there. The distances are changing. What happens if you plug t equal to 0 into this equation? If I plug t equal to 0 here, the scale factor goes to 0. The scale factor goes to 0, the distance goes to 0. So these galaxies at rest, sitting here, now have 0 distance between them. Okay? That's the Big Bang. The Big Bang is when all the distances went to 0 because the scale factor went to 0. So where did the Big Bang happen, people will ask? Well, it happened everywhere because this happens everywhere, right? So this can be an infinitely large universe having a Big Bang everywhere at the same time. Can galaxies move apart faster than the speed of light? Well, yes, they can, because they're sitting at rest. I mean, they can move here if they want. That's called the peculiar velocity. and other light can go from this galaxy to this galaxy, but they're sitting there, their movement apart is not caused by some force or something like that. It's just a scale factor can change at any speed it wants. Okay? So you have to understand this to think about. So sit and stare at this if you haven't thought about this before. Okay? Now I said that the scale factor goes like t to the 2/3. If you want to understand dark energy, you have to look at these two more equations. Okay? And this is it. Okay? These are now calculus equations, but this is r dot dr dt. This is the rate at which this, the speed at which the universe is expanding, called the rate here, r dot over r, is called the Hubble parameter, and the expansion rate today is called the Hubble constant. Okay? What's interesting is what does it depend upon? It depends on two things, the density and the curvature. Okay? So the bigger the density, the faster the universe expands. This is the expansion rate of the universe. And the other thing you want to know, if you're driving a car, you want to know how fast you're going and how fast you can accelerate. Well, there's a formula for that too. It's given here. This is the acceleration of the universe, the second derivative of the scale factor. What does it depend upon? The density, and then here's a new thing. It depends upon the pressure. Okay? So this pressure is what gives the weirdness in dark energy. Okay? That's it. That pressure term is why dark energy is so bizarre. If you want to understand dark energy, you won't be able to unless you're willing to stare at this equation a little bit. Okay? So what happened in 1917 is Einstein said, OK, let's put a uniform galaxies, which happen to have a pressure of 0. He plugged it in here, and he discovered there was no static solution. He discovered that the universe could not stand still. Okay? He didn't like this. He went back to his equations, and he said, OK, my beautiful theory of general relativity is wrong. I need to fix it. There's a mathematically valid way to fix it. He added a cosmological constant. Okay? Doing that, he could adjust these things so that the scale factor, he thought the universe wasn't expanding. The Hubble parameter he could set to 0, okay, which is what he wanted. Soon after that, Hubble, so he adjusted lambda to give a static. Soon after, Hubble found the expansion, and Einstein said, out with the cosmological term. Get rid of this cosmological constant. The universe is expanding. Mathematically, that is a allowed term. Mathematically, that is the dark energy. So Einstein was the first to consider dark energy. He put it in there, not as we see it today. He put it in there to balance the universe so it wouldn't expand. It can have that effect too. So lambda is a form of dark energy, cosmological constant. It's also exactly the equivalent of an energy density of the vacuum. Okay? So if you take energy of empty space and you put it in there, it turns out to be mathematically exactly the same as a cosmological constant. Okay? So why is it dark energy? Why does dark energy have a different effect than normal material? Well, it goes back to those equations of the scale factor. Okay? You solve the FRW equations. If you put in pressure 0, which is like cold dark matter, cold. Why do we call it cold dark matter? Cold means moving slowly, non-relativistically. That's cold. The pressure there is very small, basically close to 0. Fast dark matter, if it was moving with like a radiation, okay, then that would have more pressure and give a different expansion rate of the universe. The pressure then would be 1/3. Okay? If you plug that in, you find that with matter and radiation, normal atomic matter or photons, you find that the scale factor, the changes, the acceleration of the scale factor is less than 0. That means deceleration. If you take the energy of empty space that has a pressure equal to minus the density, you plug that in, you find that the scale factor grows exponentially, and it's an acceleration. So what people measured was an acceleration. They are assuming then, or they're going backwards using these equations to say that that means that it's a kind of a vacuum energy. Okay? Now, I'm not going to go into why vacuum energy gives negative pressure and acceleration. That's a little bit much. But all this stuff I've just said was known in the 1920s. Okay? The lambda came in and out of style. Everything changed in 1997 when this guy, Saul Perlmutter, he set out to try to find out what the acceleration, he actually measured the acceleration of the universe. He was expecting to find a deceleration, but found an acceleration. And if you go back to that equation, that meant that the density plus 3 times the pressure was less than 0. Okay, so that was the science breakthrough of the year in 1998 and the Nobel Prize last year. Okay? But what did he do? So where am I? I'm missing a slide here. I took it out for time. No. Okay. Okay. So let me just say it again because I think I took it out for time. What he did is he wanted, well, I just said it. He said that this has changed, so rho plus 3p had to be less than 0. So I'll go on because the time is short here. Okay. So there's different ways to measure this acceleration of the universe. The way that Perlmutter and the other group that shared the Nobel Prize do it is they looked for these supernovas. Okay? So you take a little picture like that, and you take a picture here, and then 3 weeks later you take another picture. They look pretty similar, but when you take the difference, you see a little dot difference, this minus this. You say, oh, there's a difference. It could be a supernova. If you look at Hubble Space Telescope, you could actually see it. Now, in fact, they can't use the Hubble Space Telescope in these early days to do it, because now they have, but because it's just such a little telescope. I mean, take such a picture of such a small area of the sky. So the beautiful thing about supernovas is that they're all about the same brightness, a certain type of supernova, supernova type 1a. They're not exactly the same, but you can fix it up by measuring how long they last and get that they're roughly, use them as standard candles. A standard candle is something that you know its brightness of. If you know how bright something is, then you can figure out how far away it is because the flux goes like 1 over the distance squared. Okay? So what you want to do is, what they do is they measure distance versus redshift. Now, why do they want to measure distance versus redshift? Well, that's what you can measure. You can measure redshift. That's easy. You just take one of those absorption lines, and then you know what silicon-2 is in the lab. You can measure silicon-2 in the supernova and see how much it's been shifted. And it turns out that that's directly related to the scale factor at the time. That's the slide I took out that I shouldn't have taken out. There's a very simple formula between the redshift and the scale factor, so that R factor can be measured directly. Okay? We can do that. Okay? So here's the plot they made. Well, this is not, they've started making this plot. This is now a very recent one, 580 supernovas of type 1a. And the point, they measure the redshift or the scale factor at the time when the light left and the distance. And this is the astronomical way of measuring distance. Why does this prove dark energy? Because what Perlmutter et al. Expected to find was that at this redshift, at this recession velocity, that this should have been much closer. If you driving in your car a certain distance, you can expect how far you've gone, and if you haven't gone as far, then you have to say, well, I guess you were going faster than I was expecting you to go. If you know how fast you're going today, you can calculate whether they would have accelerated. And in order to get to be this distance at this redshift, the universe has to be accelerating. Okay? That's how they get the acceleration, just like you say a car goes from 0 to 60 in 5 seconds. So you're really not measuring the acceleration directly. What you're measuring is distance and redshift, which is kind of a speed. So, here's the slide. Okay. So more formulas, but this is actually the same formula. This is the expansion rate, and people rewrite it into things that journalists need to understand, because this is what the cosmologists say they're trying to do. They're trying to measure different parameters. The Hubble constant, omega dark matter, omega radiation, omega vacuum. What are these omegas? That's what scientists want to talk about. Omegas are just the amount of material, the density, divided by the critical density. And we know the critical density today. It's about 5 atoms worth of material, the mass of 5 atoms in a cubic meter. So he mentioned 200 times the average density of the universe. We know the average density of the universe today. It's in every cubic meter in the entire universe, averaged over the universe, there's about 5 atoms worth, 5 AMU. That's it. Okay? That's very dense. We are very sparse, but that's the average. And if you divide that by any other material, you call that omega. So that same expansion rate is really just the Hubble constant, that's the expansion rate today, the amount of matter, the amount of radiation, and the amount of vacuum, and the amount of curvature. So these are the fundamental parameters of cosmology. If you ask cosmologists what they want to spend $1 billion for, they say they want to measure these numbers more accurately, okay? Dark energy enters as omega vacuum, or omega lambda, it's called, or a cosmological constant. It's all the same thing, okay? So that's where that comes in. Now, you cannot measure the density of the vacuum energy, okay? You can't do it. It's hard enough to measure the amount of matter and radiation, but the amount of energy in the vacuum, you can't do it. So the only way to get at it is to measure the expansion rate and use this equation, okay? Now, notice that this says that you're depending on a theory to do this. If this theory is wrong, your conclusions may be wrong. So the effort to understand the dark energy is really also a test. Is this theory here, which comes straight out of general relativity, correct or not? Okay? So one of the things we're going to try to do is test general relativity to see whether this works. Okay? And here's where I said before, the scale factor, which I keep talking about, we love it because that's a measurable. All we have to do is measure the redshift of something, and 1 over the scale factor is equal to 1 plus the redshift. So if the redshift is equal to 0, the scale factor is 1. If the redshift is equal to 2, the scale factor is 1/2. Okay? So you measure h, and then you determine these densities. Okay? That's how it's done. So you see plots like this. And journalists should look at these plots. Scientists fight over these plots. My plot's better than your plot. And when you see conflicts, they'll always just point to these plots. And so let's just take a few seconds and look at these plots. What's plotted here is the omega matter. We know that the total density of the universe is roughly equal to the critical density. That comes from the microwave background. Now, the microwave background does not really measure dark energy. Yet it's absolutely crucial in understanding dark energy. Why is that? It's because of this plot. Okay? Here's what those supernovas mean. The density of matter versus the density in the vacuum energy, which is dark energy, omega lambda. The supernova says you have to be in this region to fit that curve. Okay? They can do different models. You could fit it by here, or you could fit it by here. Quite an area, quite a difference. Omega matter between 0.2 and 0.6, dark energy between 0.6 and 0.1. Okay? But because we know the CMB, WMAP, we know that it has to lie along here. WMAP doesn't measure dark energy, but it measures the total. It measures the total, and it measures the matter. And because of that, you live along here. There's the flat universe. So we have to be, when you see these circles, it's the intersections of the circles that people are looking at. So how well you determine the cosmology, people want to know, how do you know how much dark matter there is? This is it. This is how we know how much dark matter it is. It's not from measuring the rotation curves. It's not from measuring the gravitational lensing. We convince ourselves that dark matter is there from that, but if you want to know how much there is, it's these plots, okay? And so, right. Now, why do I have 2 plots here? This is also, as journalists, I want you to look at these 2 plots and see that they're different. And this one has just statistical errors. This one includes systematic errors. And statistical errors, if you're an honest scientist, scientists will agree on that. Okay? The problem is systematic errors. These are problems of calibrations. How well do you understand the errors in your instruments? Things like that. How well are these absolute, K corrections over long periods of things done? Lots of technical things. And experimentalists almost all think that their systematic errors are better than their competitors, right? And so you have disagreements on how good your measurement is, and it's usually in here. Now, as journalists, people may show you just the statistical errors and say, look, I have the world's best measurement of dark energy. You should put me on the front page. But you need to ask, what are your systematic errors? You need to look at those, okay? They're much harder to quantify, but they are the crucial thing. And in the dark energy business, in my opinion, it's all about systematic errors now, okay? That's where the future is going to be. And people are talking about this and worrying about it, okay? So you don't do as well when you include that. So you've seen this before, and as a reporter working on cosmology, you should just memorize this diagram. Dark matter, dark energy, completely different things. Dark matter is some real stuff that's moving around. It's some kind of particle. We don't know what kind of particle it is, but it is some kind of particle. It could be primordial black holes. It could be WIMPs. It could be strongly interacting, self-interacting. We don't know, but it's stuff. Dark energy, we don't know what that is. All we know is that it's causing an accelerated universe. That's the extent of our knowledge. Okay? That's the extent of our knowledge. It could be a vacuum energy. That works. It could be something else. And notice that neutrinos and stars are about the same in importance. Okay? That's interesting to me anyway. So memorize this and just realize atoms are small. Okay? Multiple observations and lines of reasoning lead to this consensus model now. So it's not going to go away. It solves so many of the problems we have, and I won't go through them all, but there's now half a dozen or even more measurements that say that this consensus model, that pie chart, is roughly right. So we're stuck with dark energy. Of course, what we want to do is figure out what it is. Okay? The key acceleration, the key property is the acceleration. And this is controlled by this parameter W. You'll see all dark matter workers will talk about W. W is the ratio of the pressure to the density. Okay? And for regular material, this is 0. For radiation, it's 1/3. And for vacuum energy, it's -1. So we want to measure this W. So that same equation, that acceleration equation, I've written it again. Here it is, the way you write it with the things that cosmologists use. And they wrote the density of dark energy 1 plus 3W. Okay? And we want to know what that W is. So in fact, vacuum energy or cosmological constant is not the only solution. All you need is that this acceleration is positive. The matter gives a negative. The radiation gives a negative. This will give a positive only if 3W plus 1 has a minus sign. In other words, if W is less than 1/3. So we know whatever the dark energy is, if it's described with something like this, it has to have a W less than -1/3. Now, what is this W? What does a negative pressure mean? If I have a balloon full of air, it has a positive pressure. The air wants to make the balloon come out. If I have a tangled net of rubber bands and I pull on it, it will pull back. That's a negative pressure. A tangled web of rubber bands have a negative pressure because I pull and it pulls back, right? So one of the early ideas for dark energy was a tangled web of cosmic strings that when you stretch the universe, it pulls back. That's a negative pressure. Okay? Now, the remarkable thing is that quantum field theory readily predicts a negative pressure. Vacuum energy, the energy of empty space, has W equals -1 exactly. Now, why is that? If I take a box full of nothing and I stretch it and I'm getting more nothing, I have to put energy in there to conserve energy. That energy is going to make me want to go back. So it has that negative pressure. Now, why does negative pressure cause the universe to expand that way? You have to go back into Einstein's theory to do that. There's no way you're going to understand it without just staring at Einstein's theory. Okay? Now, so people like the idea that quantum field theory can easily give us this. And we know of negative pressures, huge ones. The Higgs boson, which people are searching for at LHC and probably will announce in a few weeks or months, has a basic idea of that is it fills all of space with a vacuum energy called the vacuum expectation value of the Higgs. The value of that is trillions of tons per cubic centimeter. That's really big. Okay? The actual measured vacuum energy, if you say it's a cosmological constant, is many orders of magnitudes less than that. So this is actually a problem. We know the Higgs vacuum is there. There's also other things in the QCD vacuum. So we have vacuum energy floating all over particle physics, but the measured value is way smaller by something like 120 orders of magnitude. What do you do with that? The particle physicists call this the cosmological constant problem. And Ed Witten said it was the biggest problem that he knew of. And what they have to do is cancel it out with a minus cosmological constant, a minus vacuum energy, to balance these out, because the measured one is so much smaller. So this is a big puzzle in our fundamental understanding of nature. Where does this vacuum energy come from? Okay? Now, we as cosmologists say, OK, you guys can work on that problem, but we want to give you some real information. We want to tell you what's really going on here. Is it a cosmological constant, or is it something else? So the goal of the astronomer community is to measure W now and in the past, okay? So we would like to distinguish between three broad classes of possibilities. Einstein cosmological constant. If that's the case, we know the fate of the universe. The universe is going to expand, it's starting to expand exponentially. It's going to go ever faster. The microwave background will be moving away from us faster than the speed of light. And then the galaxies that we see, distant galaxies, will move farther away from us faster than the speed of light. And eventually it's just us and our little bound area and nothing else. Okay? That's the fate if it's a cosmological constant. The other possibility we'd like to distinguish is that general relativity is correct, but there's some kind of vacuum energy that's not a cosmological constant. It's changing with time. Okay? This probably happened before in the universe. We mostly think that inflation caused the microwave background to be formed. Inflation was a vacuum energy, a cosmological constant that went away. Okay? So that could be happening again. This goes by the name of quintessence. There's hundreds of ideas. In this case, the fate of the universe depends on the detail of this new quantum field theory. We want to find out, is this real or is it this? And the third possibility, quite likely also, is that GR is wrong. If you look at string theories, extra dimensions, brane worlds, there's many different possibilities that say there is no real vacuum energy. It's that we're using the wrong theory of general relativity. We need to replace it. So this is what we'd like to do. How are we going to do it? We're going to need very precise measurements of the expansion history, and we want to find the equation of state W and whether it's changing with time. Okay? So if the density changes with time at all, it's not a cosmological constant. If W is not -1 exactly, it's not a cosmological constant. Okay? So how can we do this? This is the same equation again. I keep writing it up. Okay? This is the expansion rate, and it depends on this stuff. Okay? So we want to measure this, and there's different methods. Okay? We can use the supernova standard candles to get a distance and a redshift. We can also use a standard ruler, and the Baryon acoustic oscillation, one of the most promising methods, does that. Okay? Or you could use a standard population, like clusters. Okay? Now, this way will not let you tell you whether general relativity is right or wrong, because these kind of methods assume general relativity to work. If you want to find out whether general relativity is right or wrong, you're going to have to do something besides these three methods. So as journalists, you have to watch for this. Okay? The methods that can tell are weak lensing, and then clusters actually can do it too. Okay? So the reason you look at these different methods is they tell you different things. If you're asking different questions, you can get different answers. So let me talk a bit about Baryon acoustic oscillations. It's a very exciting new method. It's been used, and there's big plans to use it in the future. It's very much similar to the microwave background. The microwave background, there are lumps. These little blue lumps are a typical characteristic size of, say, 1 degree. That's a standard ruler. We know when this happened. We know a size. And if we can do that, we can measure the geometry of the universe that way. These lumps are areas on the sky that have certain distances on the sky are more likely to be the same temperature. If you do the same thing today, these are the fluctuations that gave rise to the density fluctuations in the galaxies. So at certain scales, you'll find also more likely to have galaxies. And that scale is 150 megaparsecs today. So you look at this bump here at 1 degree means that if you're 1 degree apart, you're more likely to have a correlation, more likely to have photons. So if you look here on the Sloan Digital Sky Survey, at a scale of 150 megaparsecs, you're more likely to have galaxies separated by 150 megaparsecs than you are at other distances. Well, here's the actual code, then here or here. Here's the actual measurements. So that bump, 150 megaparsecs, is a standard ruler. You can measure it in different redshift bins, go out different distances, measure the probability of galaxies at different separations, and at 150 megaparsecs, if you find a bump, you know that's 150 megaparsecs. You know the angle, you know the distance. You can use simple geometry to get the distance to that. So it's another way of getting the distance, like supernovas. Okay? And it's pretty clean. Okay? So in this plot, you noticed I put the BAO line here. Notice that the BAO line is different angle. This is really good because you have to, if all three of these experiments are correct, you have to be in the overlap region. And that gives you a much better determination of these parameters. Okay? So this is called complementarity. And you really want experiments that are going at different angles through these plots. Okay. So let me talk a bit about weak lensing, and then I'll sum up. Lensing, we saw, could see mass. Mass grows as the universe expands, as Elliot talked about. So if you divide the universe up into different distances and you do background things lensing foreground things, you can actually measure the growth of structure as a function of time. This is doubly good. This gives you two things if it can be made to work, because the growth of structure depends on how the universe expands, but it also depends on the strength of gravity. And if you mess with general relativity, you may actually change the strength of gravity, okay? In which case, the predictions of general relativity can be wrong in the weak lensing. The BAO and the supernovas, they can't see that because you're assuming the theory to get the distances. Here, you can measure the distances two ways. You can say you can also measure how big the lumps are, which is how strong gravity is. Okay? It's a very hard thing. You need hundreds of millions of galaxies, and the LSST experiment and some of the space telescopes that are going to be looking for the Pan-STARRS also, and the WFIRST and Euclid, they're going to be trying to use this. And these guys are the ones that can tell whether GR is correct or not. Okay? So that's just the weak lensing that I showed you before. The fourth method that has some promise, at first blush looks like it's the best, but at second blush doesn't look so good at all. And this is being used, this is clusters, okay? And this is being used by the DES survey and some other ideas. This is saying that as a function of time, or redshift, the number of clusters of given sizes is a very strong function. Clusters, it takes a long time to create a big cluster of galaxies, to grow up, right? If you change the expansion rate of the universe, when the universe expands faster, it's harder for stuff to grow. Okay? So especially on the massive end here, it's very hard to get massive clusters early on. So if you can count the number of clusters as a function of redshift, you can really get a very sensitive a measure of how the expansion rate is going. Okay? So this looked like really sensitive. The problem is systematic errors. And if you ask these guys in the DES, at first they were saying, oh, we won't have much problem. They're going to work with the South Pole telescope, a telescope to look at microwave background, using an effect called the Sunyaev-Zildovich to measure the amount of mass in there. And then they'll just do these things and they'll be really sensitive. Thinking more deeply about it, they realize that measuring that mass is really hard. And so the big problem here is, can they really measure the masses of these galaxies to put them on this plot? And if they can't, then they don't get a thing. Now, if you ask them, they've been working very hard, maybe ways to self-calibrate. And my worry about this method is they're going to come out with results, and I myself will not be able to tell how well they've been able to self-calibrate, because it's getting more and more complicated, more and more sophisticated. So you as reporters are going to have trouble understanding this, but you know at least now what to ask. You want to see how well do you know the masses of your galaxies when they start doing amazing results in dark energy. So here's the plots you're going to be seeing coming out in the literature, and that you guys are going to have to report on. This is omega matter versus W. That's what we're after, W. W minus 1, cosmological constant, okay? This is current data, that same 580 supernova type 1a plus CMB plus BAO, okay? So this is kind of state of the art, okay? So you can see that W is not that well.
It's probably worth mentioning, though, that this is today.
This is today.
We're also interested in measuring it at
yeah,
earlier time.
that comes next.
Good.
Yeah. Okay. So this is current state of the art. So I want to tell you the state of the art. You can measure W from this. It's 1.01 plus or minus 0.07. It's consistent with the cosmological constant. Okay, that's the most popular idea, but it's not that well constrained, and you still have lots of room for a non-cosmological constant. And notice it depends upon the omega matter. If you can measure omega matter better, you could reduce the errors. So other experiments that have nothing to do directly with dark energy actually are very important. If we can find some other way to find omega matter, that will really help. Okay? Finally, these limits on W assumed that W was not changing with time. Now, we have no evidence of that. Okay? In fact, the best evidence we have, the best measurement, is right here from the same group. Here's the W minus 1 with WA, which is the derivative, the change of it. This is hardly measured at all, okay? And if you allow W to change with time, the limit on W today is very weaker, okay? So we really know very little about the dark energy. So those three possibilities that I mentioned are still all completely valid. So that's the big question for the next 10, 20 years. Okay, so you're going to be watching, there's like dozens and dozens of experiments. Here's some of them that I think are going to be doing good jobs. Dark Energy Survey is going to come out, Pan-STARRS. BOSS is the extension of the Sloan Digital Sky Survey. They're going to do a much better job at BAO. And Big BOSS, if it's funded, will do an even better job. There's lots of supernovas. The Planck CMB is not going to do direct dark energy, but it's going to measure those other parameters better and have a direct effect. There's lots. LSST is going to do the weak lensing. We have these space missions, plus dozens of others. There's literally dozens and dozens of large collaborations working on this. They want to measure W and WA. So there's 4 promising methods. We can probably get a factor of 10 increase in precision. I think a lot of people think a space mission will be necessary. But the last thing I want to leave you with is the potential philosophical problem that you as journalists and the public will have to deal with. And the question is, how accurately do we need to measure this W? We would like to know the fate of the universe. We'd like to know whether it's a cosmological constant or not. At first, we want to know that, at least. And if general relativity is wrong, we want to know that, okay? But you can't prove that W is equal to minus 1 exactly. No matter how well you measure it, it still could not be minus 1. So if it was not minus 1, or if WA, the change, was not 0, even by a small amount, that would be great. We know the exponential expansion may stop and the fate of the universe will be different. Okay? So we want to get there. But suppose we measure it close to minus 1. How much do you want to spend to get it another factor a few closer? That's a difficult question, because already the experiments being considered are reaching near $1 billion. Okay? Going beyond that, I don't know. Now, the reason this has come up so much recently is there's quite a number, and I think a growing number of people, who think we don't need to measure W at all. Why? Because they think we know it. They say it's minus 1. We know it's a cosmological constant. Many people will say this with confidence. Okay? Why do they think that? It's connected to this anthropic principle and the landscape idea from string theory. I can't go into that now. If you want to talk about it, we can. But that's a very interesting debate going on in the community, and that's going to spread out into society because we're talking about billions of dollars. So I'll stop there. Yeah.
Yeah, you mentioned landscape theory, and you also mentioned extra dimensions twice, once with dark matter and once with dark energy. Could you say a few words about how extra dimensions could help? So the problem of dark energy and dark matter?
Yeah, you could, for instance, suppose there's an extra 5th dimension. How do extra dimensions change these things? That's one of the possibilities we want to test. Okay? There are many theories that explain dark energy, not by adding a vacuum energy, but by adding, say, an extra dimension. How can that help? If you have an extra dimension, we live in 3 spatial dimensions plus 1 time. If you add extra space, typically in string theory, gravity goes out into the extra dimension, but the rest of us don't. We're stuck in these 3. That means gravity gets weaker on large scales. If gravity gets weaker on large scales, it changes the expansion of the universe. It changes general relativity. And in fact, there's theories that can look just like the dark energy, can explain the data, but have an extra dimension like that. So that's a very physically different reality. One is not just an energy of empty space. The other is there's really an extra 4th spatial dimension that the gravity is leaking away from. That's one example. There's many others. Yes?
Can you talk about the role of computing in this research?
So computing here. Yeah, could you talk about the role of computing? So I tried to give you more like an underground thing, I mean like a grounding in it, but computing is incredibly, LSST has got a huge problem in computing, right? So they've got so much data coming in. All this stuff, analyzing this data is just really, that's where the challenge will be amongst others. Joel probably has other answers about computing.
Let me just give you an example of what we're doing.
Yeah, to understand
What
the,
we're doing is we're then populating all of these with galaxies
Yeah.
that have the correct distribution of luminosity of galaxies and so on that correspond to what you see, but with positions and velocities that are different depending on the cosmological assumptions.
yeah, so the basic idea is that you have to calibrate your experiment. You have to calibrate, to understand what your experiment is, you have to do simulations. And in particle physics, they actually do this. They actually,
So we're doing exactly the same thing,
Yeah.
for example, with our energy theory. It's already been done. The observers have been given these artificial universes and challenged to figure out what the assumptions were that went into them. As of last week, they have totally failed miserably. But it's okay, because the projects haven't started yet. And we hope that within maybe 6 months or
so a way to think of this that might be helpful.
But the point is that we can give them artificial universes that they can then try to understand. And as Kim said, we've been doing this kind of thing for decades in particle physics, where we do what we call Monte Carloing the experiment before you build it.
Yeah, so in particle experiments, the way to think about it is in particle experiments, at the same time they make their detectors, which seem like the big things, they start their Monte Carlos because you cannot understand the data. It's so complicated without having huge simulations of the data. So that's, a lot of people are doing that. And also, there's a lot of computing in the experiment itself. Other questions? Yeah.
All these groups are using the same Hubble and Keck telescopes. Why are systematic errors such a big concern?
So that's a great question. Every one of those techniques, okay, yeah, if they're all using the same telescopes, Keck and Hubble, why are systematic errors such a concern? They're not all using the same telescopes, but the main thing is the different techniques have different systematic errors. So in the cluster technique, well, in the weak lensing technique, you measure the bending, but you also measure not just what you're trying to measure, but everything in front of it. So you have to take that into account. In the Baryon Acoustic oscillation method, you have to really understand how the probabilities should be as according by the theory. So you need the simulations. So the supernovas, all the supernovas are not exactly the same. Even if you're using the same telescope to measure the brightness of the supernova, like HST, the supernovas are not all really the same brightness. And the question is, are different types of supernovas different brightnesses? That's a systematic error. So the methods have very different systematic errors. Yes?
Do you have a good analogy for the standing still idea? Being standing still with the scales changing in between you?
Yeah, so the way the classic one is you take a raisin bread, and you have raisins in it, which is galaxies, and you put it in the oven, and it rises. So the raisins are sitting still with respect to the bread, but the bread is getting bigger. So in general relativity, space-time can be curved. In a sense, you can say it's stretching. But there's not stretching into anything else. So in general relativity, I can have a little area here, and in fact, this is one idea about how the universe got created. You have a little area here. If you get uniform density in there, such that the FRW equations hold, that could do exponential expansion. It could still fit in this room, and yet it could be a light year across. Okay? Because if that region of space-time, the FRW equation held, the metric would be like that. The metric would be changing inside here, but not outside here. So you just have to change your idea of space-time. We're not moving in this background of space. Space itself is some kind of a thing.